In our previous lecture, we saw how from a given circuit we obtain its graph, and then how using that graph we obtain minimal representation of the constraints imposed on the circuit by Kirchhoff's current law. Okay. In particular, that representation gave rise to a matrix that we call reduced incidence matrix. And we're going to start today's lecture with analyzing the relation of that matrix to the branch voltages. Now, that up to this point in our graph theoretical investigations, we haven't yet talked about the voltages. We only consider the currents. Okay, let's study this relation through our previous example. Let me quickly draw that graph. Okay. This was our toy example with 4 nodes and 6 branches. Okay. And this is how we label the nodes and branches. Node 3, node 4, 1, 2, 3, 4, 5, 6. They were our branches, and the directions were like this: 4, 5, and 6. Okay. Then if you write KCL, which we did, in all 4 nodes, and express what you obtain using a matrix, the incidence matrix appears, and then we saw that the rows of that incidence matrix are linearly independent. Therefore, that representation is not minimal. To make it minimal, we removed one of the rows corresponding to an arbitrary node, and that node was the 4th node in our example. Okay. So to indicate that, let's put this ground sign. Okay, so that we know that this is our reference node. Reference node. We chose to obtain reduced incidence matrix A from the original larger incidence matrix. Okay. Let's quickly write down what reduced incidence matrix was. Okay. Now, for this example, it's n-1 by B matrix. N is number of nodes, n-1 is, which is 4 in this case, therefore n-1 is 3. And we have 6 branches, therefore this should be a 3 by 6 matrix. Okay. And for each node there corresponds a row. Okay. For the first node we have the first row, and the first row, like all other rows, have entries either 1, -1, or 0. Okay. So you look at the node, okay, the corresponding node, let's say the first node. Associated branches are 1, 2, and 6. Okay, so that means 3, 4, and 5 entries, 3, 4, and 5 must be 0. And 1 and 2, they're outgoing, and 6 is incoming, therefore the entries for 1 and 2 will be +1, and for 6 will be -1. So that means we have 1, 1 for 1 and 2, 0, 0, 0 for 3, 4, and 5, and finally for 6 we have -1. Okay. Likewise, -1, 0, -1, 1, 0, 0 for the second node or the second row, and finally for the third row we have 0, -1, 1, 0, 1, 0. Okay, this is a 3 by 6 matrix. Okay, now let's start talking about the branch voltages and, more importantly, the node voltages and their relation. Okay, so we have some new definitions that we need to introduce. By branch voltage we mean the following. branch voltages we can label them. We have, okay, we label the currents as I1, I2 up to I6. Those are our branch currents, and naturally we label the branch, or we denote the branch voltages by V1, V2 up to V6. V6, okay. And what we mean by V1 is this voltage here between node 1 and node 2, where branch 1 appears. Okay? And the polarity is such that when we measure that voltage, we put plus here and minus here. Okay, so here we have the positive labeled terminal and this negative labeled terminal. In other words, we have by V1 we mean V voltage between first and second nodes, because branch number 1 appears between first node and second node, and the direction is from first node to second node. Therefore, here we have 1 here and 2 here. Okay. Voltage between node 1, which is our positive label terminal, and node 2, which is negative label. Okay. And V2 is the voltage between first node and third node, V1, 3, and so on. And V6 is this voltage, which is the voltage between fourth node and first node, V4, V1. Okay, so that's how we define the node voltages. How about, the branch voltages? Now we also introduce a new voltage called node voltage. Node voltages. Okay. The letter E is generally used, okay, conventionally to indicate the node voltages, and to each non-reference or non-ground node we assign a voltage, okay, and those voltages we call node voltages. Now here we have 3 non-reference nodes, namely 1, 2, and 3. Note that fourth node is ground non-reference node, therefore we don't assign any node voltage to that particular node. So since we have 3 non-reference nodes, that means we have 3 node voltages. Let's call them E1, E2, and E3. Now the question is, how are they defined or how are they measured? E1 simply is defined as the voltage between node number 1 and reference node. And reference node is node number 4, therefore E1 is V14. Okay. And E2 is V24 between node 2 and reference node. And finally E3 is the voltage between third and reference nodes. Okay, that's V34. Okay. Now, thanks to KVL, okay, thanks to KVL, we can thanks to KVL, each branch voltage can be expressed in terms of node voltages. Okay, each branch voltage can be written in terms of node voltages. Example, let's express branch voltage 1 in terms of node voltages, that is in terms of these 3 numbers. Okay. So V1 is by definition the voltage between first and second node. Okay. This we can write as, thanks to path independence when talking about the voltage, This we can write as V1 4 plus V4 2. Okay. This equals V1 4 minus V2 4 because V4 2 is minus V2 4. And by definition, this is node voltage 1 and that's node voltage. Therefore, V1 equals E1 minus E2. That's the difference between first and second node voltages. Likewise, V5 is directly E3. Okay. E3 minus E4, but E4 is not defined. But if you had to define E4, E4 would be V44. Since the beginning of that point, I would say, by definition, E4 is 0. Therefore, we don't need to express it, we don't need to represent it by some symbol. Okay. V5 is directly E3. E6 is what? Is minus E1 because the direction is from reference node to 1. E3 is, V3 is E3 minus E2 and so on. Okay, so every branch voltage we can represent in terms of node voltages. So let's do that, and then once we have all those voltages, that set of equations, let's put that in matrix form, and once we do that, we'll see something quite remarkable. Okay. Okay. Now, what we will do now is we're going to express every voltage. We have already did one here, the first one. Every branch voltage in terms of node voltage. So V1 equals E1 minus E2. Here is the demonstration. How about V2? This is the second branch voltage. It's between first and third nodes. Therefore, it's E1 minus E3. Okay. And V3 is E3 minus E2. Okay. V4 is E2 minus E4. Okay, but E4 is 0, therefore V4 is really E2. And V5 is E3. And finally, V6 is minus E1. So here on the left-hand side we have the voltages, on the right-hand side we have the node voltages. Okay, the branch voltages here, node voltages there. Therefore, branch voltages and node voltages, they're defined, they are related to one another in a linear fashion. Let's write that relation in matrix form. Okay, put in matrix form. Put in matrix form, by which we mean we're going to find the relation between node voltage vectors and branch voltage vectors. Okay. So let's put the branch voltages into this vector, which we call the branch voltage vector. Okay. V1 up to V6, and then they are related to node voltages E1, E2, E3, and that this makes our node voltage vector. Okay. Because every branch voltage can be represented in terms of node voltages. And then this matrix here that appears, that between, okay, or that relates node voltages to branch voltages, that's form. And in order to figure out the answers of that matrix, all we need is here, all the equations, all the relations are here. So V1 is E1 minus E2, so that means E1 minus E2, and E3 doesn't appear in the equation, therefore the entry is 0. V2 is E1 minus E3. E1 minus E3. V3 is E3 minus E2. 0 minus 1. Okay. V4 is E2. 0, 1, 0. V5 is E3. 0, 0, 1, and V6 is minus E1. Minus 1, 0, 0. Okay. Here we have a new matrix. that relates node voltages to branch voltages. Now the question is it really new? Okay. So before that, let's label our new vectors. This is node voltage vector E. Okay. Its dimension is, or size is n-1. N is the number of nodes. Okay, this is node voltage vector. And we have this guy here, let's call it V. Its size is B, okay, number of branches. This is branch voltage vector. And this matrix here, it turns out that we don't have to give it a name because that matrix is very close related to reduced incidence matrix that we already defined. Okay? In particular, if you take the transpose of this matrix, you immediately obtain the matrix that appears here. And that's not a coincidence, that's peculiar to our example. That's true in general. This matrix here is a transpose, the transpose of the reduced incidence matrix. So that's the relation of reduced incidence matrix to the voltages, branch voltages and node voltages throughout the circuit. So, hence, let me put it here. Previously, we obtained AI equals 0. Okay, so that's how we express the constraints by KCL on the circuit in an economic way. Now we have another identity that we obtained using KVL this time. Hence we obtained V equals A transpose times E. Now a few explanations are in order here. Once we know the node voltages, we can determine all the branch voltages. So, KV output, no constraints on node voltage. Okay, by which I mean you give me any node voltages, any trio, for instance, for this example, and I can always construct a circuit with whose graph is the graph that we study, for which node voltages equal to the node voltage, the set that you gave me. Okay. And then how about the first sentence? The first sentence says that once you know the node voltages, that is, once you know this three numbers, you can immediately compute the remaining, these branch voltages, those 6 numbers. Okay. And that observation will be key when we develop one of the most powerful circuit analysis techniques, that is analysis through node voltages. Okay, that's an important observation. Now we're ready to talk about or present one of the most beautiful, most important theorems in network theory or circuit theory. Okay, and it's due to Tellegen. Tellegen's theorem. Consider two circuits that share the same graph. Okay. Let I be the current vector for one of the circuits. I1, I2, IB transpose B, the current vector from circuit 1. At any given time that you measure your computer, and V be the voltage vector from the other circuit. Okay, branch voltage vector from circuit 2. Then those two vectors, well, clearly they must have the same size, because they're coming from, although they're coming from different circuits, those two circuits, they share the same graph. Same graph means both circuits have the same number of branches. That means this vector and that vector, they must be the same size. Since they're same size, the inner product is meaningful. And if you compute that inner product, no matter how different those two circuits are, provided that they have the same graph, that inner product or that product is always 0. Okay. And now this peculiar fact has a very straightforward proof, and it goes as follows. Okay. Now I transpose V. Okay. Now I transpose is a row vector, and V is a column vector, and then their product is a scalar, and that scalar must be 0. Let's show that. It is I transpose V is I transpose times the branch voltage, and the branch voltage vector, we can express them in terms of node voltages using the transpose of the reduced incidence matrix. So we have A transpose E. And then that we can write as I transpose A transpose times E. I just rewrote the same thing, only replace the parentheses. And this thing is AI transpose times E. Okay. And by KCL we know that A times I, reduced incidence matrix, times the current vector equals 0. So that means no matter what the node voltages are, the product is always 0. Okay, and that's the end of one line proof. Now it turns out that this is more than just a mathematical peculiarity. Okay? It also has some very deep physical meaning, physical interpretation. And for that, we have to remember what power was. Okay, let's put that down as remark. If by I we mean I of t and B of t, those two vectors belong to the same circuit. Okay, well, if Tellegen's theorem is true for two different circuits, clearly it must be true for the same circuit. Note the same circuit. Okay. Then we can write IT transpose VT equals 0. Okay, so this is just what we have proved, Tellegen's theorem. This inner product is 0. Now let's write this inner product as sum of scalars as follows. This is K equals 1 to B. B is number of branches. Okay. I, K, T, V, K, T. Okay. This product clearly equals I1, V1 plus I2, V2 plus I3, V3 up to IB, VB. Okay. That is the sum of powers of individual branches. Okay. So this product is the power corresponding to the kth branch, and this is the sum of powers throughout the entire circuit. Therefore, the sum of powers throughout the entire circuit must always be 0. Okay. That is the total power defined as such is always 0 in any given circuit. So that means sum of powers that are delivered, that is, the sum of the magnitude of the powers with negative sign must equal sum of powers with positive sign. Okay? And the positive power, remember, means that that component is absorbing power from the circuit. So in other words, the absorbed power must equal to the delivered power. Okay? And that's sometimes called under the name conservation of power. Okay? So that's one physical implications of the Tellegen's theorem. Okay. Now, what we will do now is we will try to. First, what we have done is we started by expressing KCL in an economic way, and that gave us the incidence matrix, and in particular the equation reduces this matrix A times branch current vector I equals 0. Now what we will do is we will try to obtain a similar analogous equation for the branch voltages. Okay, that is, we try to figure out the matrix formulation of KVL. But for that we have to introduce some new definitions regarding the graph theory. And our first definition is the definition for planar graph. Planar graph, okay. Planar graph is a graph that you can draw on board, let's say, or on a piece of paper without any crossings. Can be drawn on the plane, okay, on a two-dimensional surface in such a way that no two branches intersect, cross one another at a point unless that point is a node. That is not a node. Consider this four-node graph. Okay. 1, 2, 3, 4, and directions doesn't matter for this definition. Let's call this 5, and let's call this 6. Okay. Note that if you draw it as such, here we don't have a node here. Okay, we have only 4 nodes. 1, 2, 3, 4. There's not a node here. And if you draw it like this, it seems that branches 5 and 6 they intersect at this point. But you can always redraw this particular example so that there is no such intersection. Okay. One, 2, 5, 3, 4. Now instead of drawing 6th branch like we drew here, we can always combine these 2 nodes such 6. Note that this and that, they're the same graph, because the graph only shows what is connected to what, therefore it doesn't matter how we draw it. Since we can draw this graph as such, it's the same graph, and here we have no intersection, therefore it's a planar graph. This is a planar graph. Whereas a little bit more complicated example cannot be drawn on a plane by such a simple trick. Okay. Consider this graph with 6 nodes and branches shown, and here we have an intersection, and this is not a node. Okay. The only nodes are here at the corners. This is non-planar. Okay. Because no matter how you try to draw the branches, there will always have to be at least one intersection, and because of that intersection, this graph is non-planar. Okay. Now, the reason that we are defining planar graphs is because the method that we'll introduce only works on planar graphs. Okay. So that's a little hiccup regarding that. Also, we have to have non-separableness. Let's also define that. If a connected graph stays connected after removing any one node and all the branches attached to that node, then it's non-separable. Now, using those 2 definitions, now we're ready to introduce the matrix formulation of Arcadia. Voltage law. Okay. Let G be a planar non-separable graph. Okay. Mesh matrix M is an L by B matrix. Where L is the number of inner meshes. We'll define what we mean by an inner mesh soon. And B is the number of branches. And matrix is defined as follows. Okay, its definition is, qualitatively speaking, very similar to the definition of the incidence matrix or the reduced incidence matrix. Nij, the ith row, jth column entry of the matrix M is defined as follows. Okay, the entries could either be +1, -1, or 0. They are +1 if jth branch belongs to ith mesh and their directions are in the same direction. Okay, and their directions coincide. It's -1 if the directions are opposite to one another, and if it's 0 if the branch doesn't belong to the corresponding mesh. Okay. -1 if jth branch belongs to ith mesh and their directions are opposite. Okay, and if neither of those two cases hold, then the entry is 0 otherwise. Okay, now let's try to understand what we mean by that definition. Okay, and for that we have to define inner mesh, and I'm going to define inner mesh over a graph, example graph. Okay. Example. Consider the graph that we have been working with all along. Now we no longer have to label the nodes at this point. Okay. So the branch labelings stay the same. 3, 4, 5, and 6. Now by mesh or inner mesh, what we mean all those loops, okay, closed paths. Okay. And the closed path should be such that inside it there isn't anything else. The inside is empty. For instance, this 2 is the outside one is also a closed path. It's a loop, but it's not an inner mesh because inside we have branches instead. But here we have an inner mesh because we have this loop and inside is empty. Here we have another loop, inside is empty, therefore that's an inner mesh. And finally here we have a loop and inside is empty. So we have therefore 1, 2, 3, 3 inner meshes. Note that I want to emphasize that the inner meshes, they depend on how you draw the graph. Had we drawn this graph in a different way, then we would have different inner meshes. Okay? But suppose that this drawing is given to us, and now we are to determine inner meshes. So let's do that. We have 1, 2, 3 inner meshes, and those meshes, inner meshes, they also have a direction. Direction is arbitrary, but usually what we do is we adopt the convention, and according to convention, direction is clockwise, our convention. Okay, so let's call this mesh 1. Let's call this inner mesh 2, and let's call this inner mesh 3. And the directions are clockwise by convention. Okay, so it's in the direction of mesh 1. This is the direction of mesh 2, and here this is the direction of mesh 3. Okay. So inner meshes, therefore, are 1, 2, 3 labeled or defined as in the figure. Okay. And as we said, directions are chosen clockwise by convention. Okay. Now we have the meshes, the directions, the labels, everything. Therefore, we're now ready to construct the mesh matrix using this definition here. Okay. So, M is our mesh matrix. And it will have 6 columns, because 6 is the number of our branches, and it will have 3 rows, because 3 is the number of our inner meshes. 1, 2, 3. Okay. 1, 2, 3. Okay, these are inner meshes. Okay. The first inner mesh corresponds to first row, to the second mesh corresponds to second row, and so on. And we have 4, 5, 6 for each branch that corresponds a column. Okay, now let's fill in entries. Branches. Let's fill in entries according to this definition. Okay, let's look at the first row or the first mesh. Associated to first mesh, we have 3 branches, or related to first mesh, we have 3 branches, 1, 2, and 3. So that means 4, 5, 6, they don't belong to mesh 1, okay, or they don't touch mesh 1, and the corresponding entries must be 0, 4, 5, 6. So 1, 2, 3, they belong to mesh 1, therefore the entries will be either +1 or -1. It's +1 if the directions coincide, -1 otherwise. So here, this is the clockwise direction of the mesh 1. It's going like that, so it's opposing direction of 1. So we put a -1 here, and then it reaches branch 2, and they're going in the same direction. So +1 for branch 2, and finally it touches branch 3, and their directions are the same. Therefore, +1 for third branch also. For the second mesh, we have 3, 4, 5. That means 1, 2, and 6. Those branches, they do not touch second mesh. 1, 2, 6. 1, 2, 6. The corresponding entries must be 0. Now, 3, 4, 5 touches mesh 2, and the direction of mesh 2 opposes branch 3. It's in the same direction with branch 5, and it opposes branch 4. Therefore, -1, -1, and +1 are the entries. And finally, for the third mesh, we have 1, 0, 0, 1, 0, 1. Okay, that's how we construct the mesh matrix. And now, what's the relation of that matrix to KVM, or in particular, the branch voltages? It's not difficult to see. Let me write it down. if you write KVL, and to be able to write KVL, all you need is a loop, a closed path. Let's write KVL at first, second, and third meshes. If you write KVL at the first mesh, what we have is minus V1 plus V2 plus V3 equals 0. Okay, if you write KVL at second mesh, minus V3, okay, plus V5, and then minus V4 equals 0. And if you write KVL only third inner mesh, you have V1 plus V4, excuse me, okay, and finally plus V6 equals 0. And these three equations, it's not easy, it's not difficult to see that, they're close related to that matrix. And how they're related is as follows. Let V, V1, V2, V, E transpose be the branch voltage vector. Then, as is clear from this set of equations, then n times V equals 0 by KVL, by Kirchhoff's voltage law. Okay. So that's somehow analogous to the equation that we obtained for KCL, which was reducing this matrix times current vector equals 0. A times I equals 0. Okay. Now finally, let's also find another use for this matrix, for this mesh matrix, and for that we have to introduce one less quantity vector, which we're going to call the mesh current. Okay. So to each mesh, that corresponds a mesh current. Which is related to the branch currents as follows. These were our inner meshes, or meshes from now on, and to each mesh we now assign a current. Okay, I sub 1, I sub 2, and here we have I sub 3. Okay, mesh currents, and their directions are clockwise. Now we're not defining here their physical meaning, the physical meaning of mesh currents, but for those of you who are interested in their physical meanings, there's a handout in the course web page. You can go and read them. Okay. For now, let's define them in a little bit more theoretical way. Okay. Now here we define mesh currents where they're flowing in the inner meshes, and now we're going to relate the mesh currents to branch currents, and the relation is as follows. Okay. We have I1 equals something, I2 equals something, I3 equals something, I4, I5, and I6. Okay. Now each branch current we will now define in terms of mesh currents, and the relation is as follows. Okay. Now Here we have branch 1, and here this is our branch current, okay, corresponding to that branch. Now this branch, branch number 1, touches two meshes, mesh 1 and mesh 3, okay. Now its direction is as follows. Its direction is in the same direction with mesh 3, and it's in the opposite direction with mesh 1. Therefore we write I1 equals I3 minus I1. Okay. Same with I3 and opposite to I1. How about I2, second branch current? It touches only one of the inner meshes, and its direction is the same. Therefore we directly write I1. Okay, for I2. For I3, it touches two meshes, 1 and 2. Its direction is same with I1 and it's opposite to I2. Therefore we write I1 minus I2. Okay. And for I4, it's here, same with I3 and opposite to I2. So we have I3 minus I2. For 5, it touches only mesh number 2 and its direction is the same, so we have I2. And finally, for I6, it touches only mesh 3 and its direction is the same, so we have I3. Okay. And then we have I1, I2, I3, I4, I5, I6 equals some matrix times I1, I2, I3. Okay. On the left hand side we have the branch currents, on the right hand side we have the mesh currents, and there is a matrix that relates one set to the other. Okay. If you fill in the entries of that matrix, and those entries will be coming directly from those set of equations, you will notice that here we have what? Minus 1, 0, 1. Here we have 1, 0, 0. Here we have 1, minus 1, 0. Here we have what? 0, minus 1, 1. 0, 1, 0. 0, 0, 1. Okay. Then once we write down the entries, we immediately notice that this matrix is no other than a transpose of our mesh matrix. Okay. This is here. M transpose. And this we call mesh current vector, and this is our branch current vector I. Okay. So I is branch current vector, and IN is the mesh current vector. Okay. So aside from its use in economic expression of KVL, mesh matrix also appears in this very nice relation between the mesh currents and the branch currents. Okay. Let's put that down. I equals N transpose I sub N. Now, okay, so that's, and that by that we have ended the matrix formation of KVL using the mesh matrix. Okay. In our next lecture, we'll try to introduce some new. We will talk very briefly about some other formulations where we don't need the assumption that the graph is planar, okay, which was necessary in order for us to obtain the mesh matrix. Thank you.